Hey dudes, in this video we're going to talk about simplifying and operating with radical expressions. And I'm going to drop that voice back to the teacher voice. And a radical, first off, is an expression, and it has different parts to it. So you have the radical symbol, the index, which we'll get talking more about the index in a minute, and then the radicand is what is inside the radical. So the index essentially tells us the groups of the products of a number, the number of numbers or the number of terms I need from a value to simplify. And so let's look at that. If I wanted to simplify a radical, I have to look at the index. And again, that index tells us the numbers of the same number that we need. And what I mean by that is if we don't have an index here, we can assume that the index is 2, the square root. And so a square root, when we think of it, we think of the perfect square, so the square root of 16 is 4. And the reason for that is because 4 squared, or 4 times 4, is 16. So with ones that aren't perfect squares, we have to break them up. And I'm going to do them with what's called a factor tree. For many who start out with simplifying radicals, it'll be easier to simplify with a factor tree. So 12 can be broken up into the products of 4 and 3. And then right off the bat, we see 4 is a perfect square. And what I mean by that is there's a group of 2 2's. And the index kind of tells us how many numbers I need in a group in order to simplify it out. So the square root of 4 is 2, and what's left in the radical would be root 3. And so the square root of 12 would simplify into simplest radical form to root 3. The next example is the cube root of 24. So 24 can be broken down into 12 and 2, 6 and 2, and then 6 can be broken down into 3 and 2. So again, I could have broken it down into I could have broken it down in any different number of factors, but I did this so that we could see the group of 3 2's, and that index of 3 tells us that I need 3 2's in order to simplify. And I'm left with root 3. So I could have simplified it into 8 and 3, and then the cube root of 8 is 2 to see it, but again, I wanted to make sure we broke it down to see all the different factors. So now the fourth root of 48, I can break 48 up into 12 and 4, and 4 into 2 and 2, 12 into 6 and 2, and then 6 into 3 and 2. And then from there I can see I need numbers of 4, so a group of 4 2's, and so a 2 can be simplified out of this radical, and I would be left with the fourth root of 3. So each of these give you examples of taking these radicals based off the index and simplifying them down. So now that we do that, let's look at operating with radicals. So when I'm adding and subtracting radical expressions, I need to have the same radical. A lot of times when we've done it with polynomials, you have to combine like terms. So like x squared plus x can't combine because there are not like terms. Same with here is root 5, whatever's in the radical, you can consider it as a variable or as a what creates a like term in terms of radical. So and then orders operations apply. So 4 root 5 plus 2 root 5 would simplify to 6 root 5. And then 6 root 5 minus 3 root 5 would simplify to 3 root 5, which is what this would simplify down to. So now let's say we have an expression where we don't have a common radical, a common like term, for instance. So the way we'd break that up is to simplify first. So 64 and 10, and then I believe the cube root of 64 is 4. We could again break it down to a factors tree, but if we know our multiplication facts, we can kind of think of them a little quicker. And so the cube root of 64 is 4. And so if I simplify a 4 out, don't forget the 3, because this is saying 3 times the radical, and then I'm left with the cube root of 10. Well, this simplifies further to 12 cube root 10. 270 can be simplified 27 and 10, and I know that the cube root of 27 is 3, because 3 times 3 times 3, or 3 cubed, would be 27. So I can simplify a 3 out of the radical, and I would be left with cube root of 10, which simplifies further to 2 and 3 to give me 6 cube root 10. Now, notice now my cubed root has like terms, or the radicand is the same. So being cube root of 10, I can now simplify by adding these outer coefficients, 12 and 6, to get 18 cube root 10. So the last example that we're going to look at is multiplying with radicals. So the first example of multiplying with radicals, now addition and subtraction, we need a common radicand. However, with multiplying radicals, we can multiply within the radicands and then simplify, or simplify and then multiply. Either way, I think what's more efficient is to multiply your radicands and then simplify out. So, for instance, 8 times 32, as long as the indexes are the same, we can multiply. And same goes for simplifying. We can only simplify like terms. And so I get the fourth root of 256. And so then from there, I would need to figure out a way to simplify 256. And so I'm going to, at this point, guess and check and say 256 can be broken up into 64 and 4. And 64 can be broken up into 16 and 4, and 16 can be broken up into 4 and 4, and as we see, 4 groups of 4, so the fourth root of 256 is equivalent to 4. And so this has been simplified. Number 2, so now looking, we still need to we're check the indexes. The indexes are, in this case, 2. So let's go ahead and go straight into multiplying. 4 times 3 would give us the 12. And so important to note, we can multiply the coefficients and multiply the radicals and then simplify. 5 times 10 would be 50, and y times y would be y squared. So now that we've introduced a variable into simplifying radicals, it is the same concept as if you're simplifying numbers. Y squared can be broken up into y and y. The square root of y squared would just be then y. And let's continue to break up 50 into 25 and 2. Well, the square root of 25 is 5, and I'm left with root 2. And then simplify further, you get 60y root 2 as your simplified expression. Thanks for watching.